As a university teacher, I don't use notes. And I have my own equipment. Ladies and gentlemen, buonasera. That's all the Italian I will speak. And of course, it's a great honor for me to be invited by the Balzan Foundation to share some of my science with you. I know the public is very diverse, which is not so easy in a way. I got some advice from Siert Kloeting in the prize committee. No formulas. I said graphics is okay. So I try to find a balance. I'm not going to speak about the very dramatic retreat of mountain glaciers we see nowadays, because everybody speaks about it. But I want to put the role of ice, glaciers and ice caps in a slightly broader perspective, how these ice bodies shape the landscape of our planet. And as a start, we make a little hike around the globe. This is a politically correct slide, as you can see. Yeah, you have to be careful these days. So we look at different places to see if we can find traces of glacial action. This is not so far away from here. It's in the valley of the Vadretta Morteratsch in Switzerland, in the Engadine. If you walk up there, you see these funny rocks. In the glaciological literature, they're called roches moutonnées. I never could discover a sheep in this, so I call it whalebacks. I think it's more appropriate. And they are a sign of glaciers that once flew over it. And when you have an experienced eye, you can even see the direction of the flow. Interestingly enough, we find these rocks in many places on the globe. And this lower picture here is an example from the middle of the Sahara. It's quite old. Geologists are very clever people, and I'm always impressed how they can determine the ages of such rocks. But they say it's 650 million years old. But it's without doubt the result of glacial action. And there are many parts of the world where you find these. Glaciers make moraines. Maybe some of you have noticed that, especially when glaciers retreat, they become visible. But they are destroyed many times. But it's not that the information is lost. When you suspect at some place that there might have been a glacier here, just start digging, and when you find sediments that are unsorted, you can be sure it was done by a glacier. From big boulders to clay, you all find mixed in a rather chaotic way, and only glaciers do that. When such moraines go into the deep earth and litify, we call them tillites. Also, many places of the earth you can find them. This is an example from Canada, very old, 2,000 million years, so that's 2 billion years old. This is a bit more recent from Greenland. And of course, geologists have to, I should say geomorphologists have tried to map these things all around the globe. There's more drop stone structures. What's that? When glaciers flow into the ocean and icebergs form, the icebergs melt and they carry a lot of stones, a lot of material, which drops into the ocean floor. So they are embedded in the sediment. And here you can see examples of such stones. I can go on like this, but my time is limited. There are also big there's a lot of evidence that biochemical cycles that had to do with iron and with carbon dioxide were set up in some strange way at some phases of the Earth's history. And this has in the end led to the idea that in the past there were phases where the planet was totally covered by snow and ice. This is quite a spectacular proposition to make, of course, but the evidence has been accumulating, and now people talk more about a slush ball rather than a snowball, because it's likely that at some parts close to the equator or where there are hot springs, the Earth was not really fully sealed off by ice. So I make a big jump. When you collect all the material on the history of glaciers on the globe, it looks a bit like this. It's an extremely schematic picture, of course, and you can see various stages or definitions. A snowball is fairly simple to imagine. Most of the globe is covered by snow and ice. We have an ice age where we have limited coverage, but big ice sheets in North America and Scandinavia. We had one recently. Recently is only 20,000 years ago. Depends on the perspective. If I remember the talk about time, yeah. And there's an interglacial. We live in an interglacial now where we have ice sheets on Greenland and Antarctica. But many times in the history of the planet, there are no traces of ice. So the ice was exception rather than rule. But when the ice is there, it does a lot. I'll try to convince you of that. Budyko was a Russian geographer who proposed or demonstrated in the 1960s that the albedo runaway effect could produce a snowball Earth. And what do I mean by that? It's a fairly simple mechanism where ice sheets grow, increase the reflectivity of the planet, so the planet cools, ice sheets grow further, and so on. It's a kind of a runaway feedback that leads to the snowball Earth. Very interesting paper, but at the end he said, but it never happened because there's no way out. Which is not correct. Because we now know that volcanism delivers carbon dioxide to the atmosphere in reasonable amounts. And it would take about 10 million years or so to have enough carbon dioxide in the atmosphere to melt the snowball. You would need roughly a concentration of 100 times the present day. But if everything is covered by snow and ice, there's no consumption of carbon dioxide, and it just accumulates. This is perhaps, for me, the most fascinating graph or table that has ever been produced in geosciences. I can talk about it for an hour, which I won't do, of course. It is a summary of the history of climate and life over the past 70 million years. I only want to look at this curve. It's a so-called oxygen isotope record based on about 40 deep sea sediment cores where the abundance of O18 in the chalk of the sediment is measured. And it's a measure of two parameters: the deep sea ocean temperature and ice volume on the globe. Well, how does this work? Water with O18 is very sparse in the ocean, but it varies. And when you have evaporation of water from the ocean, there's a preference for the lighter water, so to say, to evaporate. So when there's a lot of deposition of ocean water in the form of an ice sheet, there will be excess O18 in the ocean. So it's a very neat measure of ice volume. But the problem is it also measures the deep sea temperature because the diffusive process in the carbon shell is temperature dependent. So what do we see? Here was especially 50 million years ago, there was the so-called Eocene climatic optimum. And after that, temperature dropped and dropped and dropped and dropped. This is a big jump. It's the formation of the Antarctic ice sheet 34 million years ago. So we see cooling, 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 and we also see that in recent times we have the coldest time in the past 50 million years. And you can also see that there's more fluctuations there. And these are the glacial cycles. So picture goes up for the past 3 million years. I have reversed the scale. And the red curve is more or less the temperature, deep sea temperature change. It's on the relative scale. And the blue curve is ice volume. And you can see from this graph that two things. The cooling has continued. The fluctuations in ice volume increase. And the duration of phases with a lot of ice increase as well. And in the end, you can see that the climate apparently is characterized by glacial cycles that last about 100,000 years. So this is 500,000 years. We have 5 cycles here. This is the last glacial maximum. And then it jumps to the present interglacial. And what is especially striking from this graph is that the growing of ice sheets is slow and the decay is fast. I hope to explain in a minute why this is. But of course there's an impact on closer by, and the lower temperatures generated by the ice age of course had their impact on more local mountain ranges, and this is a map of the cover of the Alps. I don't know if it has been termed the Alpine ice cap, I don't know. You see, it didn't reach Milano, but everything that's blue here is ice covered. And I'll come back to this picture later when I talk about the effect on the landscape. You can see big outlet glaciers, as we call them, in the regions where we now have the big, beautiful lakes. The mystery is how can small changes in insolation, because we know these exist due to the fact that the orbit of the Earth is changing, the axis of rotation is changing, the ellipticity of the orbit around the Sun is changing, and we have the precession as well. Too complicated to explain to you in a minute. Anyway, the changes in insolation at high latitudes we think are the decisive factor in generating glacial cycles. But they're small, and you can see there's not one-to-one relation between the insolation variations, the red curve, and the temperature fluctuations. This is kind of central to my ideas about how glacial cycles work. I do a bit of geophysics now. You can look at this as a north-south cross-section from the Arctic Ocean to, let's say, Milano is here. And we have a yellow dashed line, which we call the equilibrium line. Above the yellow line, there's more snowfall than melt. More snowfall in winter than melt in summer. Below it's the opposite. And you can think of the equilibrium line as a parameter, as a level, in fact, in the atmosphere. It goes up when there's more radiation, comes down when there's less radiation. So you can imagine if I have a mountain plateau here, and this yellow line comes down, at some point it hits the mountain. And that means snow starts to accumulate. And so here on the white part is accumulation. The red bars here are the melting zones. When the ice sheet starts to grow, it gets thicker and thicker. We call that the height-mass balance feedback. So the intersection of the equilibrium line with the ice surface determines how large the ablation areas are. You can see they're quite small. So this guy keeps growing and growing and growing. And for a long time, we were not sure how we could imagine that this process could stop. But we know more about processes that act. We know that the ice sheet is warming up because the geothermal heat entering the base cannot escape. It accumulates. There's sliding over the bed, which generates energy. And so in the end, there's more and more sliding over the bed, and the ice sheet gets thinner and thinner. And that means that the melt zones increase. And if at the same time you have an insolation maximum and the equilibrium line goes up, there's no way to stop it. And the ice sheet will melt away. What is very important is the bedrock sinking. The load of the ice sheet depresses the bed. For instance, for Scandinavia, this was about 800 or 1,000 meters. And the Scandinavia is still coming up as a result of the deglaciation. So these are kind of I did not discuss all these lines in detail, but you can write an email to me, I'll send you the picture if you're interested. Yeah. So now about the effect of all this ice on the landscape. Well, this kind of summarizes it. This is maybe Scandinavia during the Ice Age, and this after the Ice Age. And huge fjords. So how can it be that ice is apparently so effective in shaping the landscape? Well, the mechanism is fairly simple. Fluvial erosion creates simple valleys which have no over-deepenings, as we say. But glacial erosion is a different story. And this is because glaciers erode the bed, and how effective this is depends on the pressure of the ice on the bed. And when the ice is thicker, the pressure is larger, and there will be more erosion. But more erosion means lower bed, thicker ice, and so on. So this is quite effective in generating deep valleys. What's happening? Yeah. So to summarize this in a graph, this is without glaciation erosion, where you see the form of a valley which evolves in time. You have to think about 10,000 or 100,000 of years. So it evolves, but it never produces any over-deepening. If you look at the situation where glaciers are active, it may start in the same way, but then you get a small over-deepening, and then the glacier gets larger, it gets deeper, and so on. So it's a huge difference in the way this works out on the landscape. It's not the ice that does the erosion, it's the rocks, the stones at the ice bedrock interface. So the stones are the tools, and the ice provides the pressure and the velocity. This is perhaps the most spectacular example. I don't know how many of you ever did a cruise in the Sognefjord in southern Norway, but it's advisable. It's very impressive. And this fjord is 1,500 meters deep. So this was probably produced by a very active glacier during many glacial cycles. I come back to that. And of course, as soon as the ice is gone, sedimentation will start. And in this particular case, there's an amount of sediment of, I think, 150 to 200 meters. So the ice flew from here to the sea. It's this fjord here. And it's really amazing that ice is so effective in carving. Yeah, and then 40 years ago was the first attempt to try to simulate this in a computer to get a more quantitative picture. And in fact, it was done by me in a very primitive way with punch cards. In that time, we did not have simple computers where you could type. And punch cards, each punch card had an instruction. You went to the operator, gave you a bunch of punch cards, waiting hours to get the output back. And then you discovered that you had a period somewhere instead of a comma, and you could do it all over again. But we learned a lot from these experiments, namely that it's quite feasible that on a time scale of a few 100,000 years, fjords can form by this mechanism. So in this model, there's interaction between ice flow, the ice temperature, because you can only have erosion when the ice slides over the bed. When it's frozen to the bed, it doesn't happen. And you have isostatic uplift. So when rock is removed and brought into the ocean, the bed will rise because there's less weight of rock. And so in that sense, glaciers not only make fjords, but also build mountains. So back to the Alps. The landscape of the Alps would look totally different if we never had any glaciers. And You can see these outlet glaciers depicted here. They all have produced wonderful lakes. Well, if you go swimming in the Lago Maggiore, you don't realize what's underneath, and that's better. But it's quite an interesting story. And I thought I'd take the effort to look for studies that have looked at the depths of these lakes and how much sediment there is. And this is an amazing picture. It's a bit slow. Yeah. So there's some lakes you know. What is in this table is the depth of the lake below the present water level. The depth of the bed. I should have written bedrock. The depth of the bedrock. And then the difference, of course, is the sediment fill that happened mostly after the last ice age, which ended about 12,000 years ago. So it's fairly recent. And there's some spectacular numbers here. The champion is the Lago di Garda and the northern tip, where the bed is 1,100 meters below the surface, and the sediment fill is 860 meters, so the lake is still only a few hundred meters deep. And you can see that for the other lakes. It's really impressive. And these huge amounts of sediments were all brought there in the past 10,000 years or so. So this brings me by the role of ice sheets in creating lakes in more general. I think you can say that on the globe, 90% or maybe 95% of all lakes, freshwater lakes, have been the result of glacial erosion. There are a few big lakes like Baikal or so, which are of tectonic origin, but the big lakes in North America, Canada, Scandinavia, the Alps, other mountain ranges, Patagonia, it's all due to glacial erosion. But the lakes are filled up. I think the lakes in the Alps will be filled up by about 10 to 15,000 years from now. So, yeah, then we need another ice age to remove the sediment first and then to erode further. And I have colleagues that doubt this view because they say, yeah, but to remove the sediment, it takes forever. But as we have an example that shows the opposite. And that's Breidamakurjökull on Iceland. This glacier, Breidamakurjökull, advanced in after medieval times over pastures. This has been documented. Over 20 kilometers, more than 20 kilometers. Over flat terrain. Then little ice age came, and now the glacier starts to retreat and it forms a lake. And the Icelanders have done a lot of studies with radar and found out that underneath this glacier is a trench 250 meters deep. That means that the sediments have been eroded by a speed of 1 meter per year. And that's enough to even remove the big amount of sediment in the Lago di Garda, for instance. So I think this mechanism works. What about the future then? So we soon need another ice age to carve out our lakes again. But it looks a bit problematical because these are insolation variations at high latitude from the orbital parameters of the Earth. We can calculate that in great detail. And normally we think that an ice age starts when there's a minimum. But you can see that this is the present day, this is 600,000 years. The next insolation minimum is very weak. It's tiny, and this is because the ellipticity of the orbit around the Sun at the moment is small. This happens every 400,000 years. So it's more likely that we have to wait for the next minimum, which is about 50,000 years away. And then maybe the next ice age may start. The carbon dioxide will be gone by far after 10,000, 50,000 years. We don't worry about that. So, yeah, this then leads me to the next and final slide, I think. Yeah. It's a possibility, it's not a prediction. Oh. Too fast, yeah. So that's where we are now, in an interglacial. We will have global warming. I hope it will stay within 3 degrees, which means that perhaps the major part of the Greenland ice sheet could survive. I'm not so sure. And then we'll have a full-scale interglacial, glacial periods 70,000 years from now to remake the lakes again. And then, who knows, because this cooling trend goes on, and we don't know exactly why there are IDs, but if this continues, sooner or later we'll run into a snowball again, and everything will be reset, which is maybe a good idea. So, to finish, for me, glaciers and ice caps are kind of the heartbeat of our planet. They grow and they shrink, they grow and they shrink, and by doing so, they make the very nice, beautiful scenery we enjoy so much. Thank you. Thank you.
Thank you, Professor Oerlemans. We would like to ask you to stay a minute.
Yes.
Maybe there are questions from the public, and we are happy to take some questions.
Absolutely.
Either in Italian or in English, I think. That
Then you have to translate them.
Well, we'll try. I don't know if I have the proper vocabulary, but I will try. So, prego. Do you need the mic from me?
Can I
Just wait a second.
Yeah, my compliments to the very good speech of Professor Oerlemans. Very nice and exciting. Now, simple question. You mentioned very interesting factors that are very difficult to understand, the sun and the ellipticity, etc., and so on, which influences the situation in general to predict what is going to happen really. My question is a very simple one. What is then your prediction about the effect of the famous CO2 debate? Well, how do you see that? You gave, an extrapolation to 5 million years, but what happens in the next, let's say, 2 or 3 generations?
Yeah, I try to avoid that. I will speak also tomorrow, in my speech tomorrow, I will talk about this. But it's clear that the warming has a huge impact on the glaciers. Glaciers are very sensitive to temperature change. Roughly, a longer alpine glacier has a sensitivity, as we say, of about 1 kilometer per degree. So when you make it 1 degree warmer, the big glaciers will shrink by about 1 kilometer. And now they are already by 2.5 kilometer. So what we see in the carbon dioxide debate is that we know fairly well what's happening. Tomorrow I will show what the IPCC predicted in 1990 for the present day. And that's fairly accurate. But when it comes to regional differences of the carbon dioxide warming, it becomes more complicated. For instance, why the warming in the Alps is 2.5 times the global mean is still in debate why this is. And these regional differences have a huge impact. Whether a glacier feels a warming of 2.5 degrees or 1 degree makes a huge difference. But yeah, it happens, and the only way to stop it is to reduce carbon dioxide emissions. It's as simple as that. And there have been some attempts to protect glaciers by producing snow or cover with fleece. This works for individual glaciers, but there are 240,000 glaciers in the world, so it's kind of hard to protect them all. Is that more or less satisfactory?
Thank you.
Yeah.
Thank you so much. So, other questions? Over there.
Hi, Professor. I would like to ask you about the melting of the glaciers and the impact on the permafrost and the scenario coming from that, maybe not now in this century or next.
Permafrost, in fact, is a bigger problem than we treat in
for
glaciers.
that. Thank you.
Because people build in permafrost and have cable cars, and the slopes become unstable. Landslides are more likely to occur. We've seen examples. It's always kind of difficult to say, well, this particular landslide is due to climate change. It doesn't work like that. Because I didn't talk about this, but of course the Alps are lifted up by about 1 millimeter per year, Himalaya 1 centimeter per year, and somewhere this material is disappearing by erosion. So if we would not have landslides, the Alps would get higher and higher and higher and higher, and it's not realistic. But it looks like it's likely that landslides and similar problems will occur more frequently. Yes. It's not really my specialty, but it's likely.
Thank you. Yes, another question.
Yeah, just ask maybe the last question, Professor. How much of the change in temperature that we are facing these years can you attribute to man-made activities?
You mean the global mean temperature?
Yeah.
Yeah. It's a key question, of course. Tomorrow I will talk about the predictability of climate and how to make predictions in a system that's basically chaotic. There's always a lot of uncertainty. And there's natural variability. We know that the climate changes because of fluctuations in volcanism, solar activity, maybe long-term changes in the ocean circulation. So it's always a mixture between man-made and natural variability. But I think the warming is so strong now that it's kind of hard to explain this without the carbon dioxide effect. So the anthropogenic induced effect.
Thank you. Another, maybe the final question.
So I was struck in terms of the snowball Earth scenario. You're talking 5 million years out, and we've been hearing quite a lot in the last couple of years about how the water cycle is a bit more complicated than most of us think, that there's actually quite a lot of subsurface water, there's even water in the mantle, and you're talking about the role of the volcanology. And I guess what I'm curious to understand with the snowball Earth or the slush ball Earth scenarios, how much of that is assuming that the current water on the surface simply changes form, becomes slush or ice, or how much of it is assuming actually that the water cycle, as we understand it, breaks down a bit, and that what you're actually seeing is subsurface water and perhaps even water in the mantle that is becoming part of this snowball Earth scenario. So how dynamic is the system? Is it well, hard questions, but she said I could go last.
It's definitely outside of my competence. I'm a geophysicist or a physicist, and about the deeper processes I know very little, but it's much more complicated than we think. I like the idea of a snowball or a slush ball, but there's so much to say to this that I'm sorry, I can't answer your...
Thank you so much. Thank you.